Welcome to this explainer. Before we jump in, I want to mention right up front that this educational material is prepared by Dr. Nima Madian. Today, we are diving deep into the hidden digital brains behind industrial automation, programmable logic controllers, or PLCs. Our goal is to completely demystify how these systems work by tearing down a real, working, automated sorting system right in front of you. Ready? Let's get into it. So, here's our game plan. We're going to tackle this in 5 quick steps. First, the physical sorting system, then the I/O translation dictionary, the operational state machine, the software blueprint, and finally, an architecture summary. We are literally traveling straight from the physical world right into the digital brain of the PLC. All right, part 1, the physical sorting system. Before we introduce a single line of software logic, we really need to understand the metal and plastic we're actually trying to control. Take a look at the physical reality of our setup. This is an automated industrial counting and sorting system. You'll notice the conveyor belt moving products continuously down the line. You can see the boxes waiting to catch those items and the sensors positioned to monitor the entire flow. It's your classic factory floor setup, completely tangible, completely mechanical. Now, zooming in on this specific mechanical components doing the heavy lifting here. Products feed continuously down from that hopper at the top. As they fall, they pass microswitch MS1. This is a mechanical sensor that physically clicks to detect every single passing item. Right below that is the directional flap, labeled F. It's spring-loaded, so by default, it drops items straight into channel A. But when the solenoid, labeled S, gets powered, a piston pushes that flap over to direct items into channel B. So what does this all mean? Well, the crucial point is our operational goal. We need to route exactly 10 items into channel A. Then we need to automatically switch that flap, route exactly 20 items into channel B, and repeat that sequence seamlessly, forever. That exact 10 and 20 batching requirement is exactly what our system needs to automate. Knowing what the hardware does brings us to part 2, the I/O translation dictionary. This is where we prepare for the cognitive leap from looking at physical parts to understanding digital bits. You see, there is a fundamental disconnect we have to bridge here. The PLC cannot see a conveyor belt or a box. The physical world is full of buttons, sensors, and solenoids. But the PLC logic world? It only reads abstract binary electrical states, inputs, and it outputs power to actuators. It also uses internal memory, which exists purely inside the software. Here is our exact translation map for this system. In the physical world, our manual reset button becomes IN1 for the PLC. This overrides and resets the whole system. The physical clicking of the MS1 item detector translates to input IN2, providing our counting pulses. On the output side, the physical flap controller, the solenoid, becomes PLC output CR1. When CR1 gets energized, the flap switches to channel B. Finally, we have our internal memory. Counters C1 and C2 preset with 10 and 20 items, acting as our digital batch trackers. With our dictionary in hand, we transition into part 3, the operational state machine. Let's explore exactly how the PLC organizes these inputs and outputs into a continuous cycle. And this brilliantly illustrates that exact cycle. We start out in state 1, filling batch A. The solenoid is unpowered, the flap is sitting at position A, and the IN2 pulses make counter C1 count right up toward 10. When C1 reaches 10, boom, it hits a transition trigger. Output CR1 energizes, pivoting the flap and throwing us directly into state 2 to fill batch B. Now, IN2 pulses make counter C2 count toward 20. When C2 hits 20, it triggers a system reset. The counter's clear, CR1 drops power, the spring snaps the flap back to A, and the cycle instantly restarts. To ensure we completely grasp this before looking at the actual code, let's linearize this cyclical state machine. Step 1. Fill channel A until counter C1 equals 10. Step 2. Trigger the flap by turning on output CR1. Step 3. Fill channel B until counter C2 hits 20. And step 4. Reset the entire system. It's a perfect sequential progression. All right, we've reached the climax of our explainer. Part 4, tracing the software blueprint. We are now going to read the visual programming language that actually runs this sorting machine. PLCs are historically programmed using ladder logic, which is a visual language based on old electrical relay schematics. To read this code, you really just need a few basic rules. First, imagine power flowing continuously from the left vertical rail to the right vertical rail. The horizontal lines are called rungs, and they represent individual conditions and commands. That symbol that looks like two vertical parallel lines indicates an input, or a contact. And the parentheses symbol at the far right indicates an output, or a coil. Now, what's really fascinating here is seeing exactly how the logic executes our physical sort. We can literally trace it rung by rung. Take a look at the second rung. Every time IN2, the item sensor, pulses, it increments counter C1. Move down to the next rung. When C1 reaches its constant of 10, that contact closes, allowing power to flow straight to output CR1. That energizes the solenoid and switches the flap. On the bottom rung, IN2 continues pulsing, but now it's incrementing counter C2. When C2 reaches its constant of 20, we look back up at the first and third rungs. C2 closes contacts that trigger the reset coils for both counters. Everything clears, CR1 loses power, the flap springs back, and the whole cycle starts fresh. That was the microscopic view of the code. Now, let's zoom back out for our final part, the architecture summary and key takeaways. It's time to look at the macro view of this infinite automation loop. Let's see how this builds into a complete system architecture. It's essentially a continuous, high-speed conversation. The physical world, via the MS1 microswitch sensor, feeds pulses right into the digital world. The digital PLC logic uses its internal counters to process those pulses. Once a specific condition is met, the digital world sends a signal right back out to the physical world, triggering actuators like our flap solenoid. Physical to physical, over and over again. So you might be asking, why does this matter? Why not just use complex mechanical gears like a giant clock? The answer is software modularity. By managing these batch sizes digitally, if the factory suddenly requires a 50 to 100 split instead of 10 to 20, an engineer can update those software constants in seconds. If this were purely mechanical, you would have to shut down the line, unbolt gears, and physically rebuild the machine. Software makes manufacturing vastly cheaper and infinitely adaptable. This system perfectly highlights two essential automation principles you should definitely take away from this. First, conditional permissives. Sequential automation relies entirely on logic gates. Events cannot trigger out of turn because earlier states, like C1 hitting 10, act as required permissives for later states, like C2 starting its count. Second, self-sustaining logic. True automation requires meticulously designed auto-resetting loops that clear their own memory and physical states to run infinitely without any human intervention. Which leaves us with a pretty fascinating final thought. The very next time you hold a perfectly packaged box of goods, maybe consider the rapid, hidden dance of sensors, bits, and actuators that put it there. How much of the manufactured world around us is silently governed by this invisible, self-sustaining logic? It's pretty amazing to think about. Thanks for joining me on this teardown, and keep exploring.